I mean, it's I guess it's the first time that one of the the backbenchers of the deep community are giving a talk in this seminar series, so I'm quite honored. And I'm going to, so maybe a short introduction. So my name is Peter Bolhuis, and I'm a professor in computational chemistry, actually, in the Van Hoff Institute for Molecular Sciences in this university. And I'm also involved in the, actually the founding of DEEP, all the way from the start, I guess, from when it became, when the NWA was initiated. That's the Dutch Science Agenda, many years back, and so since then, it evolved, and I think it's very nice. I also have here ACMM because that's our Center for Multiscale Modeling. It has been around for 20 years, so I thought it was nice to put up here. But this is just a side issue. All right, so I'm going to talk a little bit of an overview talk about how you can think about creating insight in rare event dynamics in high-dimensional systems. And with that, I actually also mean molecular systems where you have many atoms and many degrees of freedom. And so if you have any questions, please, I can't see you because I don't have any, so you really have to speak up, and it's fine to interrupt because this is supposed to be a bit of an interactive seminar. So please speak up if there's a question. Okay, so let's just start, and we start with the, I'm trying to go to the next slide. It doesn't work. I can, yeah, well, yeah, I was also hoping that my remote would work, but apparently not. Okay. Okay, so this is the famous multiscale picture, and I think we should start with this because this is actually, in my opinion, the basics of emergent behavior. And so you have here a kind of a time and length scale figure, and I'm trying to now see how, can you see my cursor? Yes. Okay, so there's it's fine enough. So here's the time scale axis, and here's the length scale axis, and it's a logarithmic scale. So here are the really microscopic processes happening, and if you move along the diagonal, you can go to larger and larger scales. And of course, you have the emergent behavior all the way at large microscopic time and length scale. And the idea is, of course, that we can think of this as different levels, where you go from, well, if you start with quantum mechanics, where you think of systems as nuclei and electrons, you go to atomic levels, then to mesoscopic, and finally you end up with some continuum field theory for large-scale processes. And I mean, there's also, of course, frameworks connected to that, and these frameworks they are well developed, and I guess that everyone in the audience is familiar with this. So on the quantum level, you have a Schrödinger equation, for example. So this is the standard way of writing this. And then when you actually integrate out the electronic degrees of freedom, and you're only worried about nuclei walking around in space, you can think of Hamilton's equations. Suddenly things become deterministic. If you don't worry about the quantum behavior anymore. And then you can actually go on to coarse graining, where you integrate out the many other degrees of freedom, and you're only focusing on special selected degrees. And this is suddenly then stochastic again. So you have a noise term here. And then finally, you can go to macroscopic deterministic frameworks like the Navier-Stokes equation, where you only think about density fields. Okay, so my little movie started immediately. So this is, of course, a nice example of how you can think of a classical molecular dynamics simulations. You just have a bunch of particles in a system which undergo dynamics in time. So you have a time evolution. And this is just solving these Hamilton's equation of motion according to some sort of a interaction, or also called a force field. And this is basically the potential energy of the system in terms of the degrees of freedom. Okay, so this is the general framework. And how do we then get insight, or how do we do something then? Well, we do molecular dynamics. And this is exactly making a movie like I showed before with the little balls, but now a little bit more complex. So what we are interested in is to predict complex molecular processes, which are actually difficult to access in experiments, or actually can add to experiments and interpret experiments. And you can do all kinds of also things that are very difficult to do in experiments. And the idea is just to solve these equations of motion. So this is the famous Newton's equation of motion. This is, of course, a simpler representation of the Hamilton's equation of motion. And what you then usually also do is to, instead of constant energy, so instead of a microcanonical ensemble, you go to the canonical ensemble, so you put a thermostat. But for the most important is, of course, the potential energy, as I point out. So this is a function of V of all the coordinates in the system. And this is bold R, that is some high dimensional vector. And I mean, in a very simple protein force field, this looks like as follows. So this is approximated with bonds, with angles, with what's called dihedrals. These are torsion angles, and some non-bonded interactions, which represents the electrostatics and some van der Waals interactions, for example, in the famous Lennard-Jones form. And when you do this, of course, this has to be parameterized, and there is, of course, an enormous industry trying to do this type of things. It has been around for 40 years, 50 years. But the upshot is that we can actually do things like this. So here you have a molecular dynamics simulation of a protein, which is, well, I would say reasonably realistic, and it shows you the behavior, the time evolution of the important aspects, in this case, an active site trying to undergo a conformational transition. I'm not going to explain exactly what it's doing, because that's a whole talk by itself. Yeah.
What is the typical size of these sums? Like you sum over 5, 10?
Good point. I didn't say that, of course, but these are typical pair interactions. So in principle, it's the number of particles squared. For angles, it's, of course, if you have 3 angles, it's a local interaction, so it still goes as, do I say that right? No, I say that wrong. No, I say that wrong because this is, of course, a local interaction. So the bonds are just between the atoms. So I think it's just a local sum over each atom in its surrounding. So it scales linearly. And I think the angles also, so the first terms actually just scale linearly. It's this per term, which is really scaling badly, of course. This is has to go over the entire system. So it's an n-squared problem. Especially for long-range interactions like Coulomb interactions, you have bad scaling, but there's all kinds of numerical tricks to get around that. You can do Ewald summation, particle mesh type of. Okay, so there's a whole bunch of.
How many bonds are in that figure, for instance?
Yeah, so okay, so a typical, so this is of course only showing the protein system. So here, I think this is a small protein, so 150 residues. It's like a couple of thousand atoms. Surrounding it is water. Water takes a couple of 10,000 more atoms. So we're talking about 50,000 atoms. So this is so, and this is in 3 dimensions. So you have to sum over 150,000 degrees of freedom. So it's not something that is small. So these are large sums. Okay, so so the idea is that we can use this to get atomistic resolutions. You get equilibrium statistics. In principle, you get free energy landscapes. You get information about stable structures, maybe some transition states if you're interested in transitions, and that's the equilibrium stuff. But you can also think of time-dependent information like kinetic rates, how the process is taking place, the mechanisms, some transport properties like diffusion or viscosity or shear moduli and that kind of stuff. So that's what it can do for us, and it's very useful in that respect. But I'm going to access two major things because there are two sources of error at least. And one of them is the sampling problem. Probably you're all familiar with that. And the second one is the systematic force field problem. That is to actually, are these parameters that go in here correct, or are they reasonable, or are they trustworthy? So these are two problems. I'm going to first focus on the first one, and I'm not sure if I get to the second one. It depends on the time. All right, so here is an example of the fastest MD computer in the world. This is the Ensemble computer. It can do millisecond timescale simulation, and this sounds like very short, but in fact for MD, this is extremely long. And that's because the time step that we are doing is femtoseconds, and to actually go to milliseconds, you have to already spend, well, I can't even do it in my head, but it's 10 to the 12th orders of magnitude on these type of systems. So that's, well, a lot. So this is a dedicated machine. Usually we are sub-millisecond, so we can do a microsecond to hundreds of microseconds now. That's doable, but not more. Okay. Now you say, if I cannot do more, but I still want to do more, why don't I go to coarse graining? Now, in fact, we have already done some coarse graining when we are thinking about going from QM to MM, from quantum mechanics to molecular mechanics. We already did some integration of degrees of freedom, namely the electronic degrees of freedom. And we usually take the Born-Oppenheimer approximation. So we forget about all the electronic structure then, and only focus on the nuclei of the particles. And these are living in a 3D space. And I usually have this as a notation. So X is the high dimensional vector containing all the positions, all the momenta for all particles. So this is a 6-dimensional vector, 6n-dimensional vector, pretty high. And then we actually write it like this, just as I said before. Now here is a picture. I mean, this is of course a 2-dimensional projection, so it's you cannot do high-dimensional representations, of course. But this is a 2-dimensional representation of the potential energy landscape of such a system. It looks horrible. So particles, if you think of it, the system as a point in phase space, it can walk on this landscape, and it has to overcome barriers here, maybe there, and it can move from one state to another. And sometimes it goes into a deep well and gets trapped there, of course. This is what things typically do. And then you might say, okay, if we want to go to higher timescales, why don't we coarse grain? But the problem with the coarse graining is as follows. First, of course, I have to say what coarse graining actually is. It is an integration over the non-essential degrees of freedom. And you can formally do that as follows. So you just take the full potential. Oh, there's a minus sign missing. This is the Boltzmann average projected on some coarser variable. This is denoted Q, where Q is now a lower dimensional representation. And this is then actually written as a free energy. Okay, so I still call it U and not F, because I'm going to use the U as an effective potential in the coarse grained representation. And then, of course, suddenly you have to, because you have integrated out the degrees of freedom, you have to have put in some friction. So there is some friction because of all the degrees of freedom that are not being taken account of are now sort of hampering the system. And there is a noise or a fluctuation term. And this is now called F, but in principle, you can use the fluctuation dissipation theorem to make the classic Wiener process, for example. So now you actually have a landscape like this. So this looks much more smooth, much more nice. And you would say, okay, this is it. We should actually do this. But in general, this is actually very misleading because, first of all, coarse graining is not easy. Which degrees of freedom should be picked up and which degrees of freedom should be integrated out? It's a very hard problem. Second of all, even if you have that, you don't conserve dynamics. The dynamics is very difficult to conserve because, I mean, in principle, this fluctuating noise term is unknown. It could be, okay, the general solution is a white noise process, but who knows? Maybe it's not white noise. Maybe there's some colored noise, or maybe there are all kinds of memory terms. So here you actually assume that everything is a diffusive process, but maybe there is memory. And that's actually a very difficult problem. And in fact, one of the deep projects is with Dan Crommelin in the audience and Mauricio on this particular point. So I'm not going to talk anything further about it. I'm going to stick with the full atomistic systems, the high dimensional systems, because I think that contains all the information, and that's how you should start your emergent behavior. But then immediately you have this problem that there is this this trapping effect, and you have all these minima in this very difficult landscape. So what will happen is you can actually see, if you do a very long molecular dynamics trajectory, there is this trapping in these states, and I sort of try to indicate here that this is the case. And this is only a cartoon. This is a serious issue. I mean, sometimes this thing is trapped here for hours in real time, and that means that the computer will never escape this. So you have to do some sort of a coarse grading to actually to do something like that, or to study something like that. And what people have found out, and I think you're all familiar with that, is that you can write some sort of a chemical master equation not for the actual trajectory, but for the probability that you are in one of these states. So you now identify states. So these are these little ellipses over here, and suppose that you have some inkling about these states. You can think of these states as that you undergo a transition from this state to another state, and you actually sort of coarse grain the trajectory in this way. Now, suddenly you do have then a probabilistic stochastic equation, and we call that the master equation, and it looks like this. So suppose that you have a probability Pj to be in one of those states, and then there is a rate constant connected to the process going out of that state. And I have to be very careful what I'm doing here. Yeah, so I mean, there is of course the time, the change of the population in I is given by all the incoming processes. So this is the rate from J to I summed over all other J's. And of course you have also outgoing processes, and you have to sum over that as well. And the rate equations, or the rate constants that are coming out of that, they are the important ingredient in this type of model. Now, in principle, you can do a spectral analysis of these type of problems. So if you would have a microscopic propagator in the sense of how do you evolve from one point in phase space to the next point in phase space, you can do spectral analysis and say something about the timescales of the entire process. But that's one way of doing it. And in fact, there is a whole literature about that. And I'm not going to talk about that. I'm going to talk about how to get rate constants for a single, for a single process in this very high dimensional landscape.
Can I answer a question?
Yeah.
So how do you extract this coarse grain trajectory picture from the molecular dynamics?
Yeah, that's of course that's the aim. I mean, this is of course something that you can do in your mind or as a concept, but the whole point is to actually do this. That's the whole goal. So we would like to do this, and we would like to have a description like this, but how you do it, that's something else. So one way is to do this spectral analysis, this eigenvector approach, but then you need access to the full microscopic propagator, and you need to diagonalize, or you need to solve this problem, and this is hard by itself. So we take a simpler approach where we just say we take the underlying equations of motions. They are known, and I just showed you how you can do that, and we extract from that the rate constants from a process from going from 1 to j. That's the end.
You will explain that now.
I'm going to explain that.
Well, may I sorry, Peter, just to do I understand that identifying these states you consider to be part of the problem? Okay, identifying these states as 1 and as 2 and so on.
Yeah.
So finding out where they are in the full state space is part of the problem.
It's part of the problem, but I'm going to shuffle that under the carpet in a moment, because I want to focus on how we actually do the transition itself. But you're right; it's part of the problem, but it's usually easier than understanding the transition itself.
And are you also assuming that these states sort of occupy all of the state space, so it's a full covering of the state space, or are there also
very good question,
regions of state space that are sort of in between?
Yeah. And this is precisely what I'm aiming at. So maybe you bear with me for 2 slides, and then we'll.
Okay, sure.
Yeah, I first want to answer a couple of other points, because this is actually all about the rare event nature of these type of processes. So if we focus on a single transition between, so previously I had many transitions and many states, but for the moment we now actually focus on 2 states, so A and B, and there is this this high barrier in between, and this is actually precisely the same as this trapped system where you have one state here and another state there, and the system has to overcome this huge barrier. And the barrier is here plotted as a free energy barrier as a function of some sort of a collective variable Q. So this is now not just a coordinate in space, but a collective variable, and it could be basically anything. But if you then observe this system and you plot this Q value as a function of time, you typically see this behavior. Now, of course, in reality, in a real complex system, your MD will only cover this first part, very small, short part, but everything is happening on a much longer time scale. And this is the time scale problem, or the rare event problem. And what typically happens is that the thing oscillates here for a long time and only occasionally jumps to the other side. And what you then want, you want to understand what's going on here. And it actually jumps very quickly here. Eh? And yeah, this is typical for ray event behavior, that you stay for a long time in these stable states and occasionally jump in kind of a binary fashion between these 2 states. And what you want is really understanding what is happening there.
So one question. I see there's that little spike just before the first transition.
This one?
Yeah. So are they also sort of failed transitions?
Yeah, very good point. And I'm not going to put too much emphasis on that, but you're right. There are many failed attempts. In fact, this is the whole idea, of course, that a system undergoes thermal fluctuations over here. Occasionally, there is enough energy in the system such that it makes an attempt for overcoming this barrier, this bottleneck. But it fails because for some reason it returns and then it goes back, and it does that very many times. And of course, because this is also an equilibrium picture, you can just taking the exponent of the minus beta f gives you the probability to go there. So this type of event is related to the exponent of the barrier, or the exponent of the minus barrier.
Can I just ask, why did you say that molecular dynamics only covers the beginning? Yeah,
well, this is typical because these resonance times, they can be minutes, hours, days, years, whatever, this length of time, but your MD trajectory only covers this part, usually milliseconds, where the time scales are much, much longer. So you have to do something. Well, and what is that do something? That's enhanced sampling. And you probably are familiar with this. This is non-Boltzmann sampling. You just say, I'm constraining my my system to be, for example, on the top of the barrier. I could do that. I could just put a bias on the system, and as simple as bias is just by constraining the system to a certain point in this to a certain window in this Q space, and that will just only sample that part. And by just doing that, I greatly enhance the probability to be there. And this and all these methods that I actually point out here, and I'm not going to talk about it, they do exactly that. They force the transition. They force you to be on top of this very improbable barrier. Now, this is fine, and it's hugely successful. So all these, I mean, umbrella sampling has been around since the 70s, and it's one of the, the nicest non-Boltzmann sampling methods. But there has been many extensions and adaptations and variants. Nowadays, metadynamics is all the rage. But okay, anyway, what it requires is a good description of how you get from A to B. So you actually need a roadmap to get from A to B, certainly if it's complex. And this is called a reaction coordinate. And a reaction coordinate is just a coordinate, a collective variable consisting of, could be a combination of many small variables, many coordinates, but it brings you really from one side of this barrier to the other side. But this is problematic. And actually, this is the heart of the problem. What is a good reaction coordinate? How do you know that? And the trouble starts immediately with a very simple potential. If you have this tree, well potential, this is just the simplest that you can think of, not? And you start running around here in this state, and you are interested in going to another state, for example, this one. So this would be, so you could, if you use these type of methods, what you typically do is you force the system from one side to the other side, and then look at, for example, the free energy. Now here is a free energy, it's F again, as a function of this collective variable, and now it's called X. And we can here again do this, this projection. And what you, oh, sorry. Yeah, okay, okay, I was thinking there would be an arrow, but there's no arrow. So what happens then is that if you move from here to there, you get this free energy. And this looks okay because this barrier is something that you can use. But if you would have chosen Y, and this is very surprising in a sense, you get a completely different result. So this barrier is much, much lower. And this is purely because of the projection. And you think, okay, we can solve this, but this is unsolvable in principle in a high dimensional system. This is a huge, huge problem. And I cannot overstate that is such a huge problem. Because the choice of your X and your Y, which is of course already a combined coordinate of a combined variable, is going to be all important, and it will change your entire projected free energy. And you might say, okay, how is this possible? Because free energy is a thermodynamic average. So this is something that should be all independent of your choice of variables. This is true, but this is not a real free energy. This is a projected Landau free energy. So it's a free energy as a function of some, order parameter. And for example, in magnetism or in the Ising model, this is usually done in the form of the magnetization. And then you have a typical form like this. But if you would have chosen something else, and well, okay, I can leave it up to you what that something else is, might be looking like this, and it's completely dependent on where you, which variable you would have taken. What is the same is the integrated free energy. So this is the thermodynamic free energy that is governing the thermodynamics between these two states. Okay, I don't want to spend too much time with it. So the upshot is that these methods, they are powerful, but they have this problem of the reaction coordinate. And therefore, people have been thinking, well, we should not look at configurational sampling, we should look at trajectory sampling. And this is by now a famous picture of this type of processes. So we have this high dimensional landscape, we have these minima in this landscape, and we are interested in trajectories going from one to the other side. But there are many of those. It's not just one trajectory, there is a plethora of these. And projecting this in this way is dangerous. So we want to unbiased sampling of all these trajectories in some sort of a trajectory ensemble. Now, there's plenty of approaches that do that. I'm not going to talk about that. I think Dan Crommeling can actually point out a few more. But yeah, this is typical what's being done for these rare event type of processes. If you're interested in unbiased sampling of trajectories, it requires no a priori correction coordinate, and that's the good thing. It does require knowledge about what states you want to go to. So these blue areas here, they define the states, and you need to be able to recognize you're in such a state. Now, this is arguably much easier than really find out exactly the way through the mountainous landscape.
But in the other case, the configuration way or whatever configuration sampling, don't you also need to identify those states?
Absolutely, yeah. So there's no from here to there. You need the same type of information. Yeah. Sometimes you can get away with information of only one state, and some of the methods can sort of explore the region outside of the one state and then take it from there. Here, you actually need also to know where you're going to. So that's why it's also sometimes called a two-ended methods, two-ended algorithms, because they start somewhere and they end somewhere. Okay, so that's a very long story. I'm not sure how I'm doing on time, probably very bad. No, very bad. I'm going to skip a little bit over this. I wanted to give you a little bit of the maths, but I think we're going to skip that. So we take the path probability density. This is basically using a kind of a space-time representation. So here is the momentum space and the position space as a function of time. And you can take an initial probability and you can evolve it in a kind of a space-time fashion where this is the time stepping. And then you can identify a distribution which depends on a particular instance of this trajectory. And this can be defined for deterministic and stochastic dynamics. This is the initial, and this is the what we call the short time Markovian transition probabilities. So the assumption is that this is a Markovian transition from state point to state point. Okay, so this is the description of the transition probabilities. For example, for Brownian dynamics, they look very much like an Onsager-Mach-loop form. So this probably is familiar to you. For Newtonian, Hamiltonian dynamics, it's a delta function. It means that it's deterministic, so it must know where it goes to. So there's only one contribution in the phase space that counts to this probability. And of course, you can go from one to the other by just restricting these Gaussians to very small numbers. So this is, of course, a bit hand waving, but you can see the point. Okay, when we have defined this, we actually know what these probabilities for the path distributions look like. And now we can actually define also the probability density for observing a path from state A to state B. So we need indicator functions. So this is the trying to answer Dan's question. We know where the states are, so we can evaluate for each X in the high dimensional space, whether or not it's in A and B, or in between. And so this is not covering whole phase space. In fact, it's covering only a small part of phase space. This is covering a small part, and the rest is unknown territory. Okay, so this is what you can do. Then you can identify a restricted probability. So you take the free path probability, you restrict it from the initial to the final state. Well, you need some normalization factors, so everything is behaving properly. We use here some path integral type of notation. And what you then can do, and this is, I think, well, it's not a new idea. It's actually already very old, of course. But the idea is that we can now do importance sampling of this particular distribution. So we have a distribution, we want to understand it, so let's do importance sampling. So we take an old initial path and we do a trial move, and then we accept or reject this using Metropolis Hastings type of approaches. And here is the famous Metropolis rule for this. So this is what you can derive. So you need some generation probability and you need some path probability. So this looks already pretty complicated because if you know that the probabilities are all these combinations of all these microscopic propagators, but there is a great simplifying notion, and that is that if you use a particular proposal trial proposal, which is called a shooting move, it is starting from an initial position, and then you integrate your equations of motion forward and backward in time. You can either accept or you can reject it based on very simple criterion. It's just whether or not it's connecting A and B. Okay, so there's a lot of stuff to talk about. I'm going to skip all of that. Here are some applications. So this is a path sampling of all these processes, and they are. I mean, this is over 20 years of development. So I mean, and every application is another presentation, of course. So I think I skip over that. But I want to show you that it actually can be done, and it actually gives a lot of insight in the actual unbiased transition mechanisms. Okay, here's I'm also going to skip very quickly over that. We can do this, for example, for protein dissociation. So here is a single two proteins. So in the beginning, I had one protein. Here you see two proteins, and they had to move around. They had to dissociate from each other. This is a very unlikely process. It happens only once every second or so. And since we only have a couple of 100 nanoseconds of time, this is really a rare event. So what is then the mechanism? Now here you see it. It actually we do hundreds, or now it's up to thousands of these trajectories. Oh, sorry. And we found many different pathways, which we actually sort of put this in a cartoon type of fashion here. But then comes immediately the question, if you have all these hundreds or thousands of pathways, how do you actually identify then the important things? What is now important? And one way of doing that is to understand, for example, a transition state. And a transition state is normally thought of as a settle point in a high-dimensional surface, or a settle point in a potential energy. Right? So you have one state here, one state there, and there's a settle point with one negative eigenvalue. The rest is all positive. But this is not what it is, because in these high-dimensional systems, we have all these little bumps in the landscape, and it's really much more complicated. So we need another way of defining transition states. And that other way is called a committer. And this is a concept that I think is very interesting, and it actually is something that, can be applied to basically anything. It actually originated from Lars Onsager in the 1940s. He called it a splitting probability, which is also a nice word for doing it. But it was mostly only for chemical reactions. There are other people called it, for example, p-fold for protein folding. And since the early 2000s, it's called committer. And this committer function is just identifying a probability for a certain phase space point X, or configurational space core point. This is a high dimensional point that a trajectory initiated from this point will actually relax to the final state, to the state of interest, as opposed to any other state. In this case, it's A and B. So here you see it's about 50-50. And this is exactly what we call a transition state. So the transition state is something which is in between two valleys, or two. So if you would, you imagine you're in the Alps or a big mountain ridge, and you have on the one side Italy and the other side Switzerland or something. And there is the transition state right on the ridge. It's also called the dividing surface. Of course, that's a low dimensional landscape. In the high dimensions, this is the way to define it. Now you can do that then for many of these pathways, and you can identify these high dimensional points as a separatrix or a dividing surface, and that's called the transition state ensemble. And in fact, and I should actually emphasize this, we can actually also have committers over here. They are lower committers, and they're here they're higher committers than a half. And this means that it's actually really a good description of the reaction. It actually predicts exactly, or via this function, of course, the future of the process. Yeah? So what is the probability to go to B? So that's actually why it is called the reaction coordinate. Okay. So in fact, it's going to be a very important function. And we can now do, and suddenly we have a little bit of a handle on how to actually go from this high dimensional trajectories to something lower dimensional. And this is actually the whole idea, that we want to have this high dimensional function, which is the committer. The problem with the high dimensional function is that it's very difficult to get inside, because if I have a function of something which is high dimensional, how do I understand what's going on in this function? I mean, it's nice that the computer can predict it, but we want to understand it as well. And this is the famous Wigner quote, and it's applicable here as well. So we want to have some dimensionality reduction. And the dimensionality reduction is really trying to find the best low dimensional combination that can actually reproduce this committer. Now, you must also realize that even if we would have, I mean, to just get the committer function is extremely difficult, because you need to, for each point, you need to have all these little trajectories and find out where they go. I mean, it's outrageously expensive. However, there is a saving grace, and that is that we can already, we have already a path ensemble, at least that's the idea, and each of the path ensembles were created from a single point on the path. And so these are indicated here in red. And we can see these as a committer attempt. And this means that we have information in this ensemble, which actually allows us to do an analysis to optimize this reaction coordinate R, which is a function in principle of many different collective variables. Okay, how do we do that? Now, first of all, we simplify the system to only describe diffusive dynamics, because then we can actually just say that we have a probability for a path, which is actually then just a product of the forward and backward committers. And this is indicated here. So this is a typical committer profile, low on the low end of the reaction coordinate, halfway, it's R0, and then 1 if you reach B. And of course, the product of these two functions will be maximized here. And what you then can do, you make a model for this type of behavior. Well, the simplest model is a 10H type of function or some other sig model representation. You parameterize your R as some sort of a linear combination. For example, this very simple linear polynomial here. Well, it's not it's a linear sum, I should say. And then you can just use likelihood maximization by plugging in all these functions, take the data from the TPS and optimize away, and that gives you insight. So in practice, this looks like this. So here's your blob of shooting points. The red ones go to B, the green ones go to A, and this vector is kind of the vector along that is the most important thing that happens in the dynamics. So it's kind of a principal component, but not quite because it uses the dynamical future of each of the pathways. So it's a history-dependent principal component type of way. Okay, so we can do that for our systems. It's not so important what it is. So we get angles and salt bridges and number of waters, and this actually gives very much insight. So it just gives you an idea how these protein systems look like. So here's a transition state for one transition. Here's one for another, and then we can really point out what the important thing is. It turns out to be this particular salt bridge, which has to be broken before something happens. So this is really identifying the culprit of what is going to happen to the system. And if you just look at these trajectories, you will never find out, because this is how do you do that?
So you do this after you found the committer.
Sorry, but something goes really wrong now. I'm going the wrong way. Yeah, just please ask your question. Yes.
So finding these crucial steps in this process, you do after you've already done this analysis of finding these sort of committers or these surfaces. Or...
Yeah, maybe that wasn't completely clear. So we do it it's a post-processing type of approach. So you just first collect the entire path ensemble. So it means you collect all these trajectories, and then you have them all stored in a kind of a big disk. And then you use these methods to analyze these. So you process the future of all these points. You know where they're going, and that gives you insight about what is important and what's not. So that's the idea roughly. There's lots of information that we can actually find out. We know exactly what the mobile waters are, what the role of the waters are, and this is actually also really good in explaining why certain mutation studies give certain results. So this is just a nice application. I'm going to skip over that because in view of the time, we can actually do the kinetics as well. So we can introduce a set of hyperdimensional interfaces between the two states, and this is actually governing the entire phase space again. Then we actually identify path ensembles on the interfaces, and that gives us direct and actually an exact way of computing rate constants, and it also gives us a way to reweight paths. And this reweighting path allows us to get the full path ensemble from a staged type of sampling. So for each ensemble, every color is a different ensemble. We have a certain sampling, and then we glue all this information together in a kind of a master curve. And that gives us the full reweighted path ensemble. So this is how this is going. This is using some weighted histogram analysis. This is very technical. I'm skipping over that. There is also an entire evolution of all these path sampling algorithms. So we can do efficient rate computation by TIS, transition interface sampling. We can do multiple states. That actually is similar. So you just define multiple states where you actually do state-to-state calculations, and that's similar to Markov models. In fact, this can go into the Markov model to analyze a high-dimensional multi-state system. You can improve the convergence by replica exchange. We can do all kinds of funny things with replica tricks, and then we can actually get things like a flux network. Okay, this is way too much, I tell you, but it shows you that there's a whole literature out there that can actually do understand or like sample these type of path ensembles and then also use them to gain information. So it's out there, so to speak. Yeah, here's some illustrative examples. I already point out the folding network. There is also recent work on base pair rotation. I can show you a very nice movie. Here's a DNA base pair that undergoes a transition, and this one transition can be then completely analyzed and see what it actually does and what is the important process. And here is a tour de force of a nucleation process. So this is methane nucleation. So you see out of many pathways, you see one where it actually forms a nice crystal. And this is actually a process that normally would take 30,000 years. And we see it here happening in a few seconds. And this is unbiased. So this actually means that if I would have to wait for the system to run, to spontaneously nucleate, I would have to simulate a walk clock time of 30,000 years. And now, and only once in the 30,000 years, it would overcome this barrier. And this is what it actually comes out. And this is really, according to the model at least, the way that this is happening. We can also do the rate. So this is actually showing how unlikely it is. 10 to the minus 23 is pretty unlikely. Okay, finally, I want to end with some recent work. So I told you about that reaction coordinates are important and that we want to learn about the high dimensional systems using this type of analysis. Now, of course, we can't do without machine learning nowadays. So one approach is this. We try to combine everything together in a one huge framework. So we do sampling of the transition paths, as I pointed out just in the previous slide. And we do some collecting of all these statistics using some reinforcement learning. The word deep is there, but I'm not sure it's so deep. It's just reinforcement learning. And what you can do then in such a neural network, you can learn the committer on the fly. And this is actually different from what I was just telling you, where you first have to sample the path and then do the analysis. This is together, and by that you improve also the sampling. So this is to maximize sampling efficiency and learning the committer on the fly. And then of course, everything is stored in this neural network, and then you have to sort of take it out from the neural network. And we do that, or at least one idea is to use symbolic regression to make a interpretable model from that. So you use the another machine learning method that puts together all kinds of expressions based on some features, and you get out a model for the committer. And we can try that on the methane nucleation. So here is the predicted committer versus the learned committer. It's not fantastic, but it's at least it shows good correlation. You can also look at the importance of the different features. So it turns out temperature is very important, which is, we could have thought of that because that's the thermodynamic driving force, of course. And then you can actually distill or extract a simplified model from this huge data set. And the good thing, or at least the promising thing, is that this will give you really some sort of a handle on how you would get basically a theory for these type of things. Because it puts in some global variables like temperature. You get some other global collective variables, and out comes the prediction of exactly what is going to happen to the system. And this is actually like the start for developing physical theories. How do we actually know that Arrhenius is right, for example, the Arrhenius law? Well, because it has some sort of an exponential of the barrier. And here, outcomes almost by luck or by sheer coincidence, an exponential of a temperature dependence of some sort of a collective variable gamma. And so all of this is like, it's kind of coming out automatically out of the machinery. And so I think this is actually the way forward for creating phenomenological theories from atomistic data. Okay, the summary of part one, and I think it's also the summary of the entire talk, is we can do important sampling of rare event path ensembles. It yields all this stuff, so complete paths, mechanisms, reacting coordinate, kinetics, and free energies. Didn't talk about free energy, but you can imagine you can do that as well. And the interesting point is that the velocity is completely different from what people usually do in the field. Usually people start with free energy calculations and then maybe move in the end to some mechanistic work. Here it's precisely the opposite. You start with trajectories, get mechanisms, find the kinetic rate constants, and then maybe in the end you were maybe interested in some free energy projections. I was hoping that I would, one thing is that I think the important thing is of the take-home message is that we can do dimensionality reductions of a committer, and that leads to understanding of the bottleneck. And I think I want to, for this audience, I want to say that this is applicable, in my opinion, to all dynamical processes, not only to molecular processes. So if I would have a dynamical system of a complex urban network or something like that, and I would like to know what is it exactly that some tipping point transition goes through and what is then the governing bottleneck, you can do something like this. And I think I should end with this. I have another question, I have another set of lectures on the force field optimization. And I think I can start with acknowledgements. So here's some acknowledgement from the people that actually were involved. So this is my group actually. So I especially acknowledge Arjun for his work on nucleation, Hannah for his work, her work on colloids, I didn't show. And there were all the other people involved, also the people from Frankfurt. And here's some picture from us in one of the kennels before the corona, obviously. So and there's some sponsors as well. So I thank you for your attention. So I'll take some questions.
Yeah, are there any questions? If there is, please.
Well, I can ask a question. Just zooming out a little bit. So the input is a very complex classical dynamical system, right?
Yes.
And that has some known parameters and some unknown parameters in it, I suppose. Or do you imagine, because I think that's maybe in the second part, but
Yeah.
If this input thing has unknown parameters, then obviously you have to measure things in order to determine those parameters. But is the upshot, let's assume that we have a well-defined, very complicated classical dynamical system. Let's assume that. And now we're interested in connecting the rate equations to the microscopic parameters. That was basically the endeavor. Is that?
Yeah, I guess that's a very short summary of it. Yeah. So I mean, you're absolutely right that there are unknown parameters in the force field definition. But if you have a given force field for a given system, then everything is determined. Of course, you can say this given force field, there are some errors in it, and sure, there are errors, and that's indeed that was the idea of part 2. But here we focus only on the sampling issues. In principle, if you would have infinite computing power, you could, of course, just run such a system until it covers the entire phase space. Right? This is possible in principle. In practice, this is, of course, impossible. It will never work. Right? So this is the problem, and this is something that holds in all realms of science. Yeah? If you want to get long-term behavior from microscopic simulations, you are always running against the time step problem. I think even in astrophysics, this is the case. Yeah? You try to simulate the entire universe, and people have to go through very tricky methods to do long time scales. Yeah? So this is the
it's a well-known problem.
Well-known problem, exactly. But the whole idea is that once you assume, and you're absolutely right, this is an assumption that your model is good, then the task is, what does the model really predict, and how can I get insight from this model? Because you should realize that if you just do a very large system, like this is just a small system, the one that I show here. But if you would show an entire bunch of proteins running around and doing all kinds of stuff with each other, you have no clue what to look at. How do you look at a certain set of atoms? Where do you find so you need hypothesis building. You need an idea of which parameters which features are important or not.
Yeah, I think Jan also was talking about how do you extract those constants.
Oh, Jan, maybe I did misunderstood the question.
That, like, if that was his main...
Well, this was maybe I was just trying to, what is precisely the precise question that you want to answer with these computations? So when I'm trying to, because you, well, many things that I
okay,
think,
so I did not focus on the questions because they are different from each application point of view, of course. I mean, so this was a bit of a framework talk where I tried to point out how you do this. But you're right, questions are very important, but a question that comes to mind is, can I, for example, predict the unbinding of a ligand of a protein accurately for a certain set of molecules? That would be a really important task. How do you do that? Well, first of all, you need to be able to compute it, but because this is kind of the chicken and egg, you need to know how this is happening, because otherwise, well, first of all, you don't have a grip on it. Second of all, you cannot interpret it and you cannot relate it to experiments. So you really need insight. So there's, so you want to have.
But is it correct?
Sorry, I can't hear you now.
I was just, is it correct that for let me try again. So is it correct that many of these questions, if you would be able to capture the long time dynamics in terms of a state model, that would allow you to answer many of those questions?
If you have, yeah, but that's already asking. So if you have the answer, you have the answer. Yeah, right. So that is true. If you would have a complete description of the, well, this, in this case, on this slide, there is this coarse-grained Markov model, and you are certain that all your transitions are well sampled and well predicted, then that's the answer, yes. But it's not, that's not an easy task. In many cases, and there are also other ways of constructing Markov models, as you might well know. I mean, in the end, it all boils down to, have I really, first of all, have I sampled it properly? And have I really used the right variables to look at this? That is always the case. It's always the same problem. What it's sometimes also called, yeah, in a completely different topics, completely different framework, people refer to this as, what type of metric do I need to know or to use to distinguish states, or to make sure that certain configurations are similar. So it's kind of what is similar and what is not similar, right? And how do you deal with that? I mean, it's all these type of questions.
I see. Yeah.
Okay, so I mean, it's a vast. Yeah, maybe I skimmed over a lot of things. So I'm sorry if it wasn't completely clear.
No, but that's useful. Thanks.
Yeah, I have a question. Can you hear me well?
Yes.
Yeah, Mauricio. Yeah, sure.
So I was wondering, maybe more on at the workflow level or the implementation level, when you show this simulation of the nucleation, is this just one long run simulation that you can compute and then somehow incorporate these calculations into the MD simulation, or it's more something that you stitch together after the fact?
Yeah, the movie that you showed is a single pop out of the thousands or so trajectories that we have collected. This one, it's just a single trajectory.
It's a single trajectory, okay.
Yeah. But it's, I mean, you should realize that this is a highly unlikely trajectory in a sense, because we started off with the idea that many things could try, attempt, and then fail. And you can imagine that if you would try to build such a cluster and a crystal, that actually that would be extremely unlikely, because the barrier is extremely high. It's 100 KT or something like that. And this, you will never see something in real life which is 100 KT. Okay, then you will ask yourself, is that then realistic in a physical framework, in a physical sense? Yeah, that's a different question. But
no, but I was more wondering, really at the implementation level. I guess you're really just running ND simulations and maybe discarding some of them. Yeah. So it's all done kind of on real time.
Sorry, that last part I didn't get.
So it's all done. It is all the simulation is done in real time. Like you are just.
Yeah. So this is real time, as in simulation time.
Right.
Yeah, right.
Okay.
And
thanks.
the whole point, I didn't say that, but the whole trajectory that you just show is about a microsecond. So that's so 1 microsecond. So these type of processes that happen in a microsecond. And you might say, okay, that's not short at all, a microsecond, indeed. but it's much shorter than 30,000 years. So in that sense, it's a rare event. Okay. I hope that's.
May I pose another question?
Yeah, go ahead.
So I have two, but let me stick to one for now. The whole framework that you sketch is very strongly dependent on the ability to sample a lot of trajectories, right? So I'm curious to what extent is that still a limiting factor? There's this whole menagerie of methods, right? The trajectory-based sampling that you discussed. So is that now sufficiently developed to tackle all kinds of systems? For instance, I'm thinking of especially of systems that are non-reversible. Is that still a bottleneck or not really anymore?
Okay, now you said you're thinking of reversible versus and then?
Non-reversible.
Right.
So
okay. Yeah. Okay. This is a very good point. I didn't explain that properly. So we assume, and this method for the path sampling, as I presented it, is limited to reversible dynamics. However, there are also other ways to sample pathways using irreversible or non-reversible dynamics. And I think, Dan, you're involved in many of those. So it's you know about this. But one thing, so we take for granted the microscopic reversibility of these type of things. And of course, from Hamilton's equations, we know that it's the case. So this is, the time symmetry is there. Is that answering the question? No, it's not, because you also asked about the limitations. And of course, this is limited in a sense that it's extremely expensive still to really do these type of trajectories. So what you would really want is get the same information maybe in a more efficient way or a more easy way. Yeah, and then of course this is maybe the sort of the brute force way of creating this insight. And there is indeed there are simpler methods, but they are all, I mean, they're not as general, so to speak. This is of course extremely general in a sense. You always have to do some approximation in the end, and so I didn't talk about that, but I mean, you can think of, for example, I think you also, Mauricio asked it, you can think of instead of doing long trajectories, you can do much shorter trajectories where you just use a kind of yet another Markovian model for the short time propagation, and then you stitch everything together, and you sort of make the fusing trajectories from that. That is possible if you know exactly what type of system you have. You have a good Markovian model for it. You know you have the right order parameters and collective variables. Then you can do it. And
so it requires a lot of prior knowledge.
Exactly. So I mean, so there's always the question is, what knowledge do you already have? What are you using to, and what do you want to get out of the simulation? And so there's this, and it's usually it's an iterative type of thinking. I mean, an iterative process. Okay, maybe I'm now moving into different.
Okay, thanks. I mean, we can discuss about this for endlessly, I guess. But nice stuff.
Are there more questions? Doesn't look like it, so let's thank Peter again.
All right, it's also time. It's very good. Thanks.